Over the years, advances in technology, especially in transistorized technology, has been able to convert something like this into something as small as this. Just the fraction of the size. But nevertheless, I still think that the Vidicon tube, the vacuum tube that can convert an image into electricity, is awesome.
Tanner, tech, Tanner, tech, Tanner, Tanner, tech, Tanner, tech, Tanner. Hello, this is Tanner Tech.
And today, we're going to be exploring how something called a Vidicon tube, which is similar to a CRT, was actually able to record video, and how it was used in these old cameras. We're going to be taking apart this camera and seeing how that all worked. I pre-recorded a ton of videos, and I put them on YouTube and sent them to auto-upload. So every video that's come out for the past 22 months was recorded in like the summer of 2018. So this is the first video that's been uploaded to my channel in a very long time. So I'm excited about that. This coming fall, hopefully in August, depending on this coronavirus stuff, I should be going to MIT, which is going to be awesome. So now, let's get into the video. Let's tear this thing apart. So this is the camera we're going to be taking a look at today, an old Panasonic CCTV camera. Now I found this while I was going through my closet. There were a lot of electronic bits and pieces, and I was kind of throwing some stuff away that was taking up too much space. And I saw this in the back of my closet. I think someone may have given this to me a while back. Now when I opened it up, I expected to see something like this CCD, which is the microchip found in most modern cameras. It's able to record an image or video on this little piece. But when I opened this little camera, I saw something that I didn't expect to see. I saw something that looked like a CRT in the back, a cathode ray tube. And I was a little bit confused, and so I was able to research it, and I found out that it's something called a Vidicon tube. And back in the day, cameras used something like this to record video. And it operates on a similar principle to a CRT, but a little bit different. Now this was super cool to me, just seeing how a camera is able to run off a CRT, and I knew I wanted to take this thing apart and learn more about how it works and see it better. But first of all, let's plug this in and see if it actually works. So I've got the camera hooked up, it's turned on. You can see that there's a little bit of glow in the CRT. There's probably too much light for you to see that, but the CRT is definitely glowing. The camera's connected to the oscilloscope, and I have it on the mode where I can see the frequency on here, figure out what it is, and I can see that the frequency here is 15.64 kilohertz, which is exactly the frequency used in NTSC video transmission, 15.65 kilohertz. So let's plug this into an old analog TV and see if we can get a video from this. Wow. Well, it actually seems to be working right now. See, I have it hooked up here. And if you look on the screen, you can see me. It's very interesting to think that this image is being recorded on a cathode ray tube, then transmitted over a wire, and displayed on another cathode ray tube. Now that we know it works, let's take it apart and see if we can get a closer look at the parts inside. So this is the tube itself. It was just held in by 2 screws, actually. But it looks really cool. So you can see the front. It's kind of got this shiny, dark coating on the front of the tube. That's where the image is focused on. And on the back, we have the connector and the glass, and the electron gun back in here. Let me see if I can get this out of its yoke. Wow. So this is the tube, and it is beautiful. So how this vacuum tube works, and how it is able to convert light into an electrical signal, it all starts with the optics. So we have a lens here, and this lens is similar to any other type of lens used in a normal camera, that focuses the light onto the sensor. And the sensor is this shiny part in the front. Now how the sensor is laid out is first there's a layer of glass that protects the vacuum inside it. Then you have a layer here of something called tin oxide, which is transparent and it's conductive. Then past that we have a layer of something called antimony trisulfide. And that is a photoelectric compound that is able to lose an electron when light hits it. And at the back of the tube we have some innards that are very similar to those of a normal cathode ray tube television, the electron gun. So we have a heated cathode right here, which is a coil of wire that glows and heats up this cathode, that is able to be a source of electrons. Now in front of this we have two accelerator grids, and these grids are charged to a high potential that accelerate the electrons at them through this little hole and in a beam across the vacuum tube. Now this beam is further focused by a grid that surrounds the entirety of the tube. You can see this grid right here, it's this metal part. You can see the heated cathode and the accelerator right there. This beam, when it comes out of the electron gun, is going in a straight line and only hits one point in the cathode ray tube. But to get it to move around, we have something called a yoke. That's made of two electromagnets that are able to move the beam in any direction. This is the yoke of electromagnets that surrounds the vacuum tube and bends the electron beam where it needs to go. This beam will trace across this little screen by going slowly across it, then quickly back down to the next starting point, then back across it again, then to the next starting point, and then back across, then to the next starting point, and then quickly back to the original starting point. So in this way, the beam is effectively able to trace over the entirety of the surface area of this little vacuum tube screen. Now you may be wondering, how is the scanning electron beam able to turn the image that's on this image sensor into something that, can be transmitted over wires to another television? And the answer can be found in how these layers of certain chemicals are able to interact with the light and with electricity, and how this circuit is set up. So typically, this middle layer of tin oxide is attached through some kind of wire to part of the circuit. If you look on this tube, you can see this shiny metal part right here, and this connects to that inner tin oxide layer. That tin oxide layer is then connected through a load resistor to a power supply of approximately 50 volts. When the circuit is operating, this point has a potential of 50 volts, like we discussed, and so this tin oxide layer is going to be at a potential of approximately 50 volts. Now what happens is when light hits this, it travels through the first two layers and it hits the antimony trisulfide layer. When the light hits it, it knocks off electrons proportional to how strong the light is. Now those electrons go to this positive layer and are quickly sucked away into the power supply. So there's going to be different charges on this bottom layer that look like the picture that is being focused onto the faceplate of this vacuum tube. Now here's where the fun part comes in. There's going to be an electron beam that's going to scan the different parts of this layer. Now when the scanning electron beam goes and it hits a more positively charged point on the antimony trisulfide layer, and it's more positively charged because there's more light hitting that specific point, then there's going to be more electron holes in there. So the electrons in the electron beam are going to fill in those holes and quickly be moved through the tin oxide layer and through the load resistor into the power supply, which is going to cause, because of the current flowing through here, a voltage change on this point. Now if the electron beam hits a more negatively charged point on the bottom layer, then there's not going to be as many electron holes inside there for the electrons to fill in, and therefore not much is going to happen. And there's not going to be much current that flows through the circuit. We're going to see not a high voltage on this point. And so, depending on how the different charges are on this bottom plate, we're going to see a differing pulse on this point. This is an example that might make it a little bit easier to understand. So imagine this is the image projected onto the faceplate of this vacuum tube. Now the electron beam is going to be scanning this, and as it's scanning it, this part is white. So we're going to see a high voltage on this output. This voltage is going to be high because this background is white. Now the image is going to keep scanning, and then as soon as it scans this black square in the middle, the light is going to drop. And then as soon as the beam scans to the other side where it's more white, the beam is going to come up again. And it's going to keep scanning. It's going to hit the black square, go dark again, leave the black square, go light again. And it's going to keep doing that until it gets back to the white. And so from this scanning electron beam scanning this, we get a waveform that looks something like this on the output right here. Now keep in mind that as the camera is scanning this image, it is scanning it about 30 times per second, and the amount of scan lines in here are approximately 625. Now when it comes to the circuitry of this circuit, it is able to convert this signal and align that signal with the scan rate of this. So, there you go. That is how a vacuum tube is able to convert an image into electrical pulses of electricity that are able to be either saved to a VHS tape or transmitted across the world. I really enjoyed making this video. I learned a lot about how things like this work, and I hope you did as well. So thank you for watching, and stay tuned for next time.